Hello and welcome to Lesson 8, our last lesson of Unit 1 of Calculus. Today's learning goal is to be able to determine continuity of functions at a point and over an interval using limit laws and function values. So last class, in our last lesson, we saw cases where the limit was defined for a function, even though the function itself was not defined for those values of x. We saw that when we got the indeterminate cases that the function had a restriction on the domain, but if we evaluated the left-hand side and the right-hand side limit, we were able to reach a value. And we did this by factoring methods or change a variable or rationalizing the numerator or denominator to get a value for the limit in order to predict the behavior or determine the behavior of the curve as the function is approaching or as x is approaching a specific value. Now, today we're going to make connections between the output value of a function and the limit and how that relates to continuity. So continuity is the idea of drawing a graph without lifting your pencil. So if you can draw a full curve without lifting your pencil as you draw the curve, then it is a continuous function. And that can even be over a specific interval as well. But do not confuse this with, for example, when we draw our quadratic function, you don't necessarily draw the full function. So for example, with this quadratic graph here, I drew the curve without lifting my pencil, but I didn't necessarily draw the full function. So it doesn't mean that you're drawing the full function, but whatever part of it that you're drawing, and this could be, for example, in this specific interval, then I didn't have to lift my pencil here, so this would be a continuous function. Now, to give it a more specific definition and connecting it with algebra, we say that a function f of x is continuous at a specific point. So for example, x is equal to a. If f of a is defined, so that means a is in the range, or sorry, a is in the domain of the function, and we actually have an output value at that point. And also, if the limit of x approaching a of that function exists and it actually equals to f of a. So there are, in a way, two but three conditions there because we also need this to be defined and we need it to be equal to f of a. So if those two conditions are met, we say that the function is continuous at that x value, and if not, we say it is discontinuous. And you've actually seen a lot of examples of discontinuities, and now we're just going to make connections with that limit piece. So here we have the four common discontinuities you've seen, or sorry, the three common discontinuities you've seen, as well as an example of a continuous function. So in the first example on the left, that's actually a continuous function for that given interval, so between -3 and 7. And the reason for that is I am drawing the function and I do not have to lift my pencil. Now, at any point, if you look and you try to evaluate the limit, you will see that the limit will be approaching a specific value and it'll actually be the same as the output value of the function. So whatever f of a would be. Now, alternatively, in this example, in our second example, we have a point discontinuity, and that's when you have a hole. And we saw this in our last lesson where we were able to evaluate the limit from the right-hand side as well as the left-hand side. And even looking here, you can see that the limit will be 3 approaching from either side. So here we would say, and let's define this as f of x, then we would say the limit of x approaching 1 of f of x is 3. And you can analyze this as from the right-hand side as well as from the left-hand side and make the conclusion that because they're the same, then the limit of the function as x approaches 1 is equal to 3. That being said, f of x, or sorry, f of 1 is not defined. So this does not equal f of 1. And so based on our definition of continuity, this is not a continuous function at x is equal to 1. This does not mean that the whole function is not continuous, but just at that point it is not. We can also have a jump discontinuity where and we saw this also with the example of the absolute value function, where here from the left-hand side, or okay, let me start this way. Here, f of 1 is actually defined. F of 1 is about 5.5. That being said, the limit from the left-hand side is actually 4, and the limit from the right-hand side will be that 5.5. So here, the limit does not actually exist. So even though we have a defined value for x equals 1, we still cannot say it is continuous. And you can clearly see if I try to draw this, then I have to remove my pencil here and then continue from here. And same with this function here. When I go to the hole and I reach the hole, I have to lift my pencil. I can't keep going because there's a hole there. And so that simple act of lifting your pencil makes it discontinuous. And so in this example as well, we have a discontinuity at x equals 1, and this one is a jump because you're jumping from one point to another point. And finally, we also saw this example as well, where you can have an infinite discontinuity. This is also our asymptotes. And this one is actually a vertical asymptote. And so in this case, we see that, again, the function is not defined at f of 1. And so even though we do have, and the limit actually here, hold on, I'm gonna write with the limit as x approaches 1 of f of x here is actually positive infinity. And I'm sure you can tell by now in our range, we wouldn't have a value of infinity. So even though the limit actually exists, it does not equal to our value of f of 1. So then again, we don't have a continuous function at x equals 1 here. Now let's look at another example, and we're going to do some tests for discontinuity or tests for continuity. So you're asked to look at continuity at the point x is equal to 0, 1, 2, and 5. So I'm just going to start by labeling here 1, 2, 3, 4, 5. This is x and y. And alternately, this way we have our negatives. Now let's start with x equals 0. So right away, we can actually see that the function isn't even defined here. So we don't have an output value. So f of 0 is undefined. And just to do the analysis, the limit as x approaches 0 of f of x is positive infinity. Because we can see that from both sides, we're going towards infinity and we're growing. So it's getting bigger, and so it'll be positive infinity. Now, let's look at x is 1. So here, again, I can see that f of 1 is not defined. And this is shown by that hole there. And so although, again, we have a limit, and this time the limit is actually a specific value. So here, oh, I should have labeled this. Okay, so here we can see that this is 2, and you can check that from the left-hand side this way and from the right-hand side this way, we are approaching 2. But again, because f of 1 is not defined, it is not continuous. So these ones are all no. Now let's look at 2. And just to name them as well, this one was our, I think, infinite discontinuity. Oh, this one is our point discontinuity. And now let's look at the next example. So at x is 2, f of 2 is defined. It's -2. That being said, the limit of x approaching 2 from the left-hand side is 0. We can see that here. We're approaching 0. And the limit of x approaching 2 from the right-hand side is -2. And so, because of this, we say that the limit of x approaching 2 of f of x is undefined or does not exist. I'll maybe introduce you to this. Does not exist, this acronym. And this one is now a jump discontinuity because you can see that we are jumping from one point to another. Now, let's look at x is 5. Here, f of 5 is 1. And the limit of x approaching 5 of the function, and we can see here, both from the left-hand side and the right-hand side, we are approaching 1. And so we say that then f of x is continuous at x is 5. And the reason for that is because this is equal to f of 1. Okay, so this part is really important. So this one was also no, but this one, yes, it's continuous. And I'll show you just one more point for comparison. So this one at x is -2, clearly we can see that it is continuous. You can draw without lifting the pencil pen. And same with at 5, I can draw that line, that portion at least of the function without lifting my pencil. And so we can say that f of the function is continuous at both -2 and 5. And can you think of other points where it might be continuous? There's more than one answer, especially if you're looking at decimals, you will have infinite answers. But it is clear to see which points it is not continuous for. Now, let's look at another example. Here, we're actually going to start with graphing. So starting with my, let me do this one in blue, and I'll do maybe this one in green. Okay, so x squared minus 3. So we know our x squared function, something like that, not exact. And I'm just going to remember my translations or transformations is the translation of 3 down. So that means I'm going to start over here. But this is only for values of x less than or equal to 1. So if I have 1, 2, 3, 4, 5, and same here, we're going to do 1, 2, and here we have x and y. Okay, now here you're just using key points or transform, just remembering that this is a translation of the x squared function. So I know my first point is there. And I'm actually going to stop there because it's only until, or the domain for this part is until x is equal to 1. And on this side, we have that point, and then we have this point. Oh. So we have something like that. And now, our second part, f of x is equal to x minus 1. Again, this is your y equals x function, our linear line, and it's translated 1 down and only defined for x is greater than 1. So at 1 itself, we actually have a hole there. And then we just continue. This part is just these points. If I draw my straight line there, just gonna make that a little thicker. Okay, there we go. And so you can see here the graph of this function. And now you're asked, where is this function continuous and where is it discontinuous? So I hope you can see by now, just visually, that here at x is 1, we have our discontinuity. So f of 1 is defined as by x squared minus 3, so 1 squared minus 3, and it'll be negative 2. However, the limit of x approaching 1 of f of x, this does not exist. The reason for that is from the left-hand side, we are actually approaching negative 2. From the right-hand side, we are approaching 0. And so the left-hand side and the right-hand side do not match, so the limit does not exist. And so that's actually our only discontinuity here, because anywhere else, uh, either if you're looking at x greater than 1 or x less than 1, we can see that both the quadratic function, even though it's translated down, it's still one of our quadratic functions, as well as the linear line, they're both continuous functions. I can draw both of them without lifting my pencil, and for any value that you pick on these curves, we will see that the limit of x approaching that value is equal to the output of the function at that value as well. And so if we're just writing with interval notation, I would say continuous for x in, so anything greater than 1 or, and, okay. And keep in mind here, I'm not including 1 in my value. You can also write this as continuous for x in R, just x is not equal to 1. Especially when you have one discontinuity, it's easier to write it that way as well. Just eliminate the one restriction you do have. Now you're given some functions and you're asked to test the continuity for each function at x is equal to 2. So right away, you should know that for a, it will be continuous because I just told you for quadratic functions, it will be. Now, let's just analyze it as well. Here, f of 2 is 4. And if we look at limit of x approaches 2 of x squared, this is our applying our limit laws or limit properties. We have this, and through substitution, this will just be 4. And this is equal to f of 2. And so because it is defined at that x value as well as the limit is equal to the output, then it is continuous. So check. Now for this next one, if we try to do f of 2, you will see that this is not defined because your denominator is actually going to be 0. And so this would probably, or we could predict it could be whole discontinuity. So let's just test the limit here as well. And this is a good practice of the previous lesson of evaluating limits when we have indeterminate cases. So here we can see our numerator is going to be a difference of squares. And canceling those two out, we are left with limit of x approaching 2 of x plus 2, which is through substitution 4. So if you graph this, you'll actually see that as the function is getting, like, at x is 2, the function is pretty much 4, except there will be a hole there. So we do have from the left-hand side and the right-hand side, we are approaching that 4 value, but this is not equal to f of 2 because f of 2 is not defined. So then we say this is not continuous. And now in our last example, here again, you can see right away that f of 2 is not defined because 2 is just not in our domain. And for this one as well, if you try to find the limit, you'll see that we can't do any of the techniques that we've learned because in your numerator you have 1. There's nothing that we can factor, simplify with. So this one, um, or actually, let me ask you, what kind of discontinuity do you think this will be? So I hope that this reminded you of our rational function 1 over x. And if you remember from functions, the graph of that should look something like this. And now that -2 tells me that I'm moving 2 units over to the right. And so I'll have something like this. And you can see that at when x is 0, so our x-intercept here, we have this value. And we will have a vertical or an infinite discontinuity or vertical asymptote here at x is equal to 2. And so that's also why the limit is undefined here, because we see that from one side we're going to infinity and from the left-hand side we're going to negative infinity. So left-hand side and right-hand side are not equivalent, so the limit does not exist. Okay, and for our last example today, we are asked to determine all values of x for which the following function is discontinuous. So let's look at our function first. We have 1 over x squared plus x. This is actually similar to the example above where we just saw where we have a numerator of 1. So we want to find values of x for which this function won't even be defined. And we know that when x squared plus x is not equal to 0, then we just have a simple fraction and we can actually solve uh, for the output and it'll be defined. So then the values of x squared plus x, which are equal to 0, are going to give us the undefined values for which we have a discontinuity, because we will just have that f of a will not exist. So we say does not exist when a squared plus a is equal to 0. Now, here we're just solving for values of x for which this is true, and this is just factoring. So we have x times x plus 1. So the values of x for which f of x is discontinuous are 0 and -1. And here I've included a graph for you to see as well. You can see clearly that at x is 0, and then also at x is -1. Maybe let me make these two a little smaller. So here's that 1 and or 0 and the -1. We see that we have infinite discontinuities, or again, remember these are vertical asymptotes. And so then we can conclude that the function is just discontinuous at these two values. And anywhere else, it will be defined, the function will be defined, and the limit will exist, and the limit will equal to the output, so it will be continuous. And you can see I can draw pretty much any part of this, or this side, or this bottom part, without lifting my pencil. Now, our second part here, we have f of x is equal to 1 over x squared plus 1. So here, x squared is going to be greater than or equal to 0 regardless of what value of x we have. And so then we have that this function is actually defined for all values of x, and that x squared plus 1 is greater than 1. And so again, it's defined, and if you try to evaluate the limit at any point, you'll see that it will equal to the output. So we can make that generalization that it is a continuous function. And now, as a challenge for you, I would ask you to try to figure out the values of square root of x minus 5. And if you're not sure, you can always graph the function and see what you notice from the graph itself. And so just some key ideas about continuity. So we can have a function be continuous at a point. And so what that means is that it is going to be continuous at a point x is equal to a if f of a is defined and so that means it exists, and if that limit of x approaching a of f of x is equal to that f of a. So it will be the same. And for the limit, again, we also need that limit to exist itself, so the left-hand side and right-hand side. Now, for polynomial functions, so anything with exponents that you have, those are going to actually be continuous for all values of x because there's no restriction is going to be defined. The domain will just simply be, it'll just be x is in R for the domain as well. And you'll see that the limit will hold true as well. Now, if you have a rational function, f of x, which is defined as g of x over h of x, where g of x and h of x are both polynomial functions, maybe I'll add that in there for you, then we say that f of x is continuous for all values of x in R, except where h of x is equal to 0. And we saw many examples with that. And finally, for our radical function, when you have a root, and it can be a root of any value like 2, 3, 4, it doesn't matter, it doesn't have to be a square root, then these are continuous for all values of x in R, where the value under the root is greater than or equal to 0. So here where the value of the root is g of x, then we say that our requirement is g of x has to be greater than or equal to 0, and then the function will be continuous. And just to wrap it up, when one-sided limits are not equal, and we saw this in many examples, then the limit does not exist at that point, so the function is not continuous because its limit does not exist, even if the function itself is defined at that point. And so I hope you're comfortable now with continuity, and you have some practice sets here to just practice the concepts and figuring out points of discontinuity and also types of discontinuities. And again, this was our last lesson of this unit. You have your summative for Unit 1 next lesson. And if you have any questions, please don't hesitate to reach out, and I'll see you all in Unit 2.